So live okay? Okay. Okay, so welcome all the participants to this Gian workshop. This 1 week workshop actually will be having Professor Lorenzo Pavesi, and he will be first dealing with your silicon photonics fundamentals, and then about the micro ring resonators he will be telling you. Then he will be telling how you can use micro ring resonators in optical networking. Then it's in use in optical computing. So that will be by Wednesday. Then Thursday he will be introducing quantum photonics. So how this photonic circuits you can use in quantum computing. And then he'll be talking about this inter and intra-particle entanglement and quantum random number generator using silicon photonics. And then the Friday evening session, he will talk about quantum key distribution with silicon photonics. Okay, so this first 2 days of the lecture will be about understanding silicon photonics, and then last 3 days, that is last 2 days, that is Thursday and Friday, he will tell us how quantum communication, to establish the quantum communication, you will use silicon photonics. So without understanding this, we cannot proceed with that. So the other thing is that we have 2 industry sessions during this workshop. There is, so when we talk about the course of this is silicon integrated photonic circuit for quantum communication. So we all have done a lot of quantum communication requires this encryption, that encryption, everything we have heard about. Now the thing is, if you ask anyone, how will you implement that algorithm? Okay, you have some encryption at Alice, and we will be seeing this. The first I will be introducing about photonic circuit, and the second session I will be introducing you to quantum communication. So all the quantum algorithms, you know, this BB84 protocol or DPQKD protocol, whatever they are there, that we already know. But how will we implement this? The hardware part, that is what we are trying to focus in this course basically. So as India has this national quantum mission, you know that this year has been declared as by the government. So we are trying to make a lot of progress in this quantum computing. So the biggest challenge in any machine is, for example, if you say that there is machine learning AI and they are extremely low, you are able to process large amount of data in deep learning or generative AI, who is actually working? It's a machine. What is the hardware of the machine? How will you fabricate that? So there is the software part, the algorithm part, and there is the hardware part which we deal. So here in this course, we will be focusing on the hardware part, how you are going to implement that quantum communication, how will you design a circuit. So like we already know that previously we used to write all these models on our own, but nowadays there are commercially available software. So we have 2 such softwares here in VNIT, and both of them has agreed to give a session here. One software is Numerical Interconnect, and there you can simulate photonic circuits. So we know about, you can simulate, all of you must have been doing simulation about electronic circuits, right? How do you do it? You do it in multisim, you take certain, or you have PSpice simulation. You know, every one of us do that. It's very easy. You drag and drop certain components, you connect them, and then on the DSO you can see what is your output. Okay, that is a very simple thing. Now think about this, the exact circuit now I want to design using photonic circuit. What will change is electronic circuit, the communication happens using electrons. In photonic circuit, the communication will now happen using the photons. Very simple. So now how photons, so electronic circuit, what happens? The electrons flow around the circuit and you have a current. As per your Ohm's law or Kirchhoff's current law, voltage law, whatever you have learned, you design the whole circuit. Now that whole concept you have to bring here. If it is a circuit, first of all, it has to be very compact. Right? If it is a system, a sound system like this, it will be big. But if it is a circuit, it is a chip inside the computer, it will be very compact. So the thing is, the same thing now I am trying to implement using photons. So I have to make it very compact, and I have to, what you do is, I have to design I have to simulate it first, then I have to design it, and I have to then fabricate it. That is the standard procedure in any circuit courses, whether it is an electronic circuit or a photonic circuit. You design your circuit, okay, I need to design a low pass filter using an op amp. What I will do is, I'll take an op amp, I'll connect some resistor capacitor, that is my designing. Now, is the resistor value correct? Is the capacitor value correct? Is the op amp correct? Is the voltage supply correct? How will I know it? I'll simulate it. So where do you simulate? You use a circuit simulator software. Once you simulate, you get your desired result. Next, what you will do is, you will say, okay, I want to bring it on breadboard. That is what you do once your simulation results are successful. That breadboard is a big one. When you want to bring it on a chip, what will you do is, you will go for fabrication. So remember, the process is always design, simulate, and then fabricate. Very simple. For designing, you need the concepts which we will be teaching here. For simulation, basically what we do is, we need certain circuit simulator. So for like the way you have circuit simulators in electronics, we have certain circuit simulators in photonics also. That company or that software is numerical interconnect. So that is the second half. Today we will have a workshop on that circuit simulator. The company is giving it so that you can understand how you can use it to simulate the circuit, any circuit you have. Now, what is the next third part I said is, once my simulation is successful, I will go for fabrication. So for fabrication, you have to design the layout of a circuit. So for example, this building is there. You have the layout of the building. Okay, there will be classrooms here, there will be lecture hall here, there will be labs here. That is the layout. Similarly, when you go for the fabrication, you should have the layout of your circuit. That layout designing part is called, you generate what is called as the GDS file. So for that, again, there is a software that is actually there are many softwares available in the market, but the software which we have purchased here for this designing the layout of the circuit, that software is called here Lucida Photonics. It is IPKIS. What you do is, you use Python scripting programming, and tomorrow there is a company based in Belgium. So Belgium has this IMAC fabrication lab where they fabricate photonic circuits. So if after this course you come to know that does anyone in India fabricates photonic circuits, integrated circuits? No, we do not have that capability. So if you want to get it fabricated, you have to get it fabricated from certain developed foundries which are across the world. I'll show you today in that introduction. So to submit your design to that, you need a software. That software demonstration, again, it's a Belgium-based company called Lucida Photonics, and tomorrow Lucida Photonics is going to give you a session again from 3 to 5 so that you understand how you can design the layout of the circuit. Okay, so this is how our for today and tomorrow we'll do, and the next 2 days, that is Wednesday, Thursday, what we are going to do is the protocols, and we will be learning the protocols here, we will be learning the circuit here. So then we will implement BB84 protocol using this numerical software. We will have a hands-on session where you will be designing that circuit and you will be implementing. Similarly, you have DPQKD protocol which you will be implementing in your lab. So these things we will be doing. So you will have a good idea. In the first half, you will be having a theory of your background of the course, and the second half you will have a hands-on about the softwares available, so that when you go back to your place and you decide to apply anywhere, this is what has happened to our students. They have got placed in the company. Even if you know that you have an exposure to these softwares, you can apply for certain companies for the jobs, and if there are faculties in the group, then what they can do is you can apply for projects. So nowadays, if you apply for projects saying that you are going to do the fabrication and the characterization, your chances of getting the project is very high. So that way, when they give a talk in the session, you can ask how, and academic, there is a lot of discount. So that is why they have agreed that there are academic participants here. They will display this. Yeah, okay. So I hope that everybody has a good idea about the overall layout of the course. Right? So now I know some of them, they are my students, but the others, can the participants tell me your name so that we have some idea? hear. You can be just a bit loud, or we can move around the mic, whatever you want. Satish, could you- just Priyanka, you can start.
My name is Comm Priyanka. I'm from NSUT Delhi.
She's from NSUT Delhi. You are a PhD. Just let us know.
Yes. Yeah. I am PhD scholar from in NSUT Delhi, and my topics is already is integrated photonics.
Okay. So just your name and college would be sufficient. Yeah, that is.
My name is Sunil Padole. I am from Medicaps University, Indore.
Okay, welcome, sir.
Hello everyone, good morning ma'am. My name is Satish Kumar Thakur. I am Assistant Professor in Government Engineering College, Jagdalpur. And my topic is Silicon Photonics with Quantum Communication.
Good morning everyone. I am Ashay Atkar from VNIT.
Okay. She can pass.
Good morning, everyone. Good morning, ma'am. My name is Anushka Bhope, and I'm from St. Vincent Pallotti College of Engineering and Technology, and I'm a second year engineering student. Good morning, everyone. My name is Shruti Vahane, and I'm from St. Vincent Pallotti College.
Good morning, everyone. Good morning, ma'am. I am Sanchi Bharat Kamble. I'm a second year student pursuing industrial IoT from St. Vincent Pallotti College of Engineering.
Good morning, ma'am. Good morning, everyone. My name is Achal Duse. I am from SVPCET.
Good morning, everybody. Good morning, ma'am. My name is Arya Dhoti, and I'm from SVPCET.
Good morning, ma'am. Good morning, everyone. I am from St. Vincent Pallotti College of Engineering from Department of Industrial IoT, faculty member in department.
Good morning, everyone. My name is Alpa Pandey, and I am a second year student from SVPCET.
Good morning, everyone. I am Riya Belekar from SVPCET.
Good morning, ma'am. I am Sejal Saharkar from SVPCET.
Good morning, ma'am. I am Bhumika Devtare. I am from SVPCET.
Good morning, everyone. I am Mehak Bhargav from RCOEM.
Hello, ma'am. Hello, ma'am. Hello, everyone. Myself, Krishna Pawan Sharma, and I am also from RCOEM, Nagpur.
Good morning ma'am. I am Gaurav Chudasama from RCOEM.
Good morning, everyone. I am P. Venkat Subbareddy from Department of CSC and IT Warangal.
Okay, welcome, sir.
Hello, everyone. Good morning, ma'am. I am Sumedha Desai from VNIT.
I am Preeti Khere from VNIT.
I am Rohit Patil from VNIT.
Om Gawande from VNIT.
Shubham Kumbare from VNIT.
Jay from VNIT.
Good morning, ma'am. I am Bhakti Dandge from VNIT.
I am Samrundi Bhoyar from VNIT.
I am Tanu Ramteke from VNIT.
Myself, Vaibhav from TGPCET, currently in third year student.
Good morning, everyone. My name is Navina and I am from VNIT.
Good morning, all. My name is Manasa Devarkonda and I am from VNIT.
Good morning, everyone. I am Mansi from VNIT.
Good morning, everyone. I am Anupam Verma from VNIT.
Myself, I am Bharat from VNIT.
Good morning, everyone. I am Priya from VNIT.
So it was nice knowing all of you. At least now we know the names of and who is who here. So now we'll start with this. Just one. The screen is visible, or should we switch off the slide? It's visible. So this is the notes. After this, once the lectures are over, we'll be providing you access to all the course material and whatever it is over here. Okay. So rest assured of that. So like I told you, this is notes we have prepared about this, what is photonic integrated circuit. So the first thing that is important in the background about this concept of photonic integrated circuit is that the foundries which were there for electronic circuits, what happened is that they also started like this. You know, you have those semiconductor foundries coming up in India also. In Gujarat, they are coming up. So basically, how did it start in the 1960s is that there is this concept of multi-project wafer. So what did they do is, the students were like, you all are doing your electronic circuits, now you simulate. Now what the faculty said is that we will have one chip, and on that chip, what we are going to do is we are going to integrate all your circuits on that chip and get it fabricated. And then once the chip, so chip is a die, it's a 8-inch die in which a designated area is given to all the students or all the participants. So once the students got to know that, okay, the circuit which I am simulating, I can also fabricate and test it. So then what happened is immediately your interest will go high. So then that concept became very successful, and slowly this electronic industry foundry started coming up. Similarly here in this photonic industry also, now the foundry where you fabricate your electronic ICs, similar, they are known as CMOS foundry. The CMOS stands for anybody? Complementary metal oxide semiconductor. So here you will see that the foundry is the same. The foundry which we use for electronic IC manufacturing, that is the IMEC which is giving the presentation tomorrow. The same foundry we can use for photonic ICs fabrication. Why? Because the material, we will see it as we progress along the courses, the material that we use for fabricating the electronic chip, the same materials are used for fabricating photonic key. So there you have SiO2 and silicon. Here also we have SiO2 and silicon. So that is the advantage, was that once your foundry is ready, what was the advantage now? Your manufacturing factory is ready. You do not have to set up the factory again. The same factory which is manufacturing one type of chip, that factory is now going to manufacture another type of chip. So what happens is that it is very easy to implement. See, if you have to set up a foundry from the scratch, it is very challenging. But if you have a ready-made foundry and you just have to change the dimension of the components and everything, then that is easy to do. So that is how this whole thing started in this year 70s, 80s, 90s. So the commercialization, if you see here in point 2.4 here, I have written the commercialization of silicon photonics in 2000 revolutionized the field. Its compatibility with CMOS manufacturing process, that was the biggest advantage that we had when we decided to come in this field of photonic integrated circuit. What was the advantage? Was that first thing is your foundry was compatible, whether it was an electronic IC or whether it was a photonic IC. Then one more thing that we'll come to here is, why are we going for this photonic ICs? It's not just the quantum computing, but why in general is, forget the second part of the course, that is quantum communication. Let's just focus on why are we going for this photonic in ICs, or it's a very new concept. If you tell anyone that I am attending a course which is on photonic integrated circuit, then the question they will ask is, what is photonic circuits? All we know about is electronic circuits, right? That is the first thing that people are going to tell you. So the question that arises is, why are we going for this photonic circuits? Anybody? Think over it. Somehow you have all heard about that Moore's law, right? The number of transistors is doubling every 2 years on a chip. It was given in 1960s. So the number of components that you are integrating on an IC, we are going from VLSI, that is very large scale integration. What is happening? Somewhere along the line in electronics domain, we are reaching a saturation. So then what is the next option that you have to find out is, like for example, if these you have these renewable sources of energy and non-renewable sources of energy. Why did we start exploring solar as a source of energy? Why? Because coal is getting exhausted. So we decided that what is the next? So in last 10 years, government invested a lot. Let's invest a lot in solar energy, solar power solutions. And nowadays, every household also has it, right? We have these solar powers in our home where we can use it and they generate enough electricity for the whole house, the whole building, right? Similarly, that is the concept here is somewhere along the line, they are realizing that electronic chips might get saturated. They have a limit. So what is the next is from electron you go to the next level is your photons. So that is one of the main reason why all the companies, whether it is Intel, Qualcomm, they are all getting involved in this, and that is why this field is getting commercialized. That is the most important reason here. Okay, so now once, so see here it is this that since 2010 we have a lot of these advanced platforms like quantum computing, 6G, AI everywhere. This photonic circuit is coming into play. And what is the biggest is that we can actually fabricate now that photonic IC. Once you can fabricate, if it was only a theoretical concept, it would not have come here. But like I told you, with the exposure to the softwares and all, you can actually come and fabricate it. So that's why this concept is now becoming a very, and those of you who want to, usko utha lo na. Yes. So those of you who want to work in this field, this is for your masters and PhD. It is a very emerging and good area. So one thing about your is that most of you are MTech PhD students. When you go for research, you have to take new topics of research. We all know that. When you do studies or when you study any topic, you study in your textbooks and all. When you study something, for example, you studied in high school, you studied Newton's law and all. Newton's law 100 years back was a research topic that you do, and then slowly it comes into the textbook and you all study what is a cell, what is a mitochondria, what is Newton's law, what is thermodynamics principle. Once upon a time it was a topic of research. Once it became so popular and so commonly used that every man started using it, it became a part of your textbook. So there is the difference between your textbook and your research. Research, you take up the topics which are very latest or very current, so that people have not worked in it that much. So you can work on it and you can publish papers in it. So this area of silicon photonics, quantum computing, these are very good and new latest emerging areas. And you already know about it that there is this PMRF, I think this budget government has announced that Prime Minister's Research Fellowship. There you are getting almost 1 lakh of research grant so as to pursue PhD in India. So when you decide to pursue PhD, you will always be confused which topic should I take. So at that time when you explore it, this is one good topic you can explore because this is a very nascent or a new emerging field. Okay. Okay, now so I hope that with this you have a good idea about this photonic components, photonic circuit and its background. Right, you go through it tomorrow again. Professor Pavesi will give you he's from Europe, and they have really made a very big progress in this field. One of the advantage why Europe is making a progress in this field is that they form always a group and work together. So, or sort of a consortium you can say. So, for example, I know the software, but I don't have the fabrication. And let's say he's in Italy, he has the software knowledge, and somebody in Belgium has the hardware. They both will collaborate and make sure that the idea which is there in their brain immediately gets fabricated. That is how the end-to-end things. So that is another thing I want to tell you all is that if you all have great ideas or good ideas, do not just keep it to yourself. Try collaborating with people. Okay, the problem is, let's say your institute can provide you with certain amount of resources. You feel that yes, beyond this I want more resources. You can always look up to the institutes, like for Nagpur you have VNIT here. Similarly, on national level you have IITs, IIScs, and nowadays IIT Madras, IIT Bombay. You can just collaborate with all of them and make sure that somehow your idea comes into materializes. It just not remains in its original state. That is very big reason why Europe has made such a progress. He'll tell you how, and he has been working in this field for 30 years, so that's why he has a very good expertise. Today I'll be giving you his review paper also. He has written a recent review paper, 30 years in silicon photonics, and you can see how he has experience from a young lecturer in the 90s to a full professor here, and he is also the director of Quantum at Trento. So that is a European Union funded scheme where he has set up a quantum center at Trento University, and he is currently the director of that. So he'll tell you the details about that. So now, as you know that this circuit, now you have understood that this field is making a lot of progress and everything. Now coming to again the basics of it. How will you design a circuit, right? That is the first thing I told you. The three parts we have is your design, your simulation, and your fabrication. Fabrication and simulation, we are doing it in the second half. First half is what your designing part. Now if I tell you to design an electronic circuit, you have a full background in electronics, you will immediately say, I'll take this component, that component, and design it. How will you design a photonic circuit? You will say that, ma'am, I don't know any components in that. That is the first thing. What is an equivalent of a wire in if it is an electronic circuit, you will have wires, right, in which the currents will flow. How will the photons flow in a photonic circuit? That is the question you will ask. There has to be some path, a guided wave, medium, in which it will flow. Then only I can have that, okay, photon I want to send from here to there. I need a path. What is that guided path? If for electrons, we know that there are wires and you have your waveguides and you have your chip circuit, everything. Photons, what will you do? So the first component, that's why we have it, is your waveguides. So your waveguides, I'll be dealing about the waveguide again. I'll be teaching you again in the second half, the second part of the lecture is that how the waveguide works is, the waveguides are basically, you have to remember is, it's a literal English word is, it is guiding waves. So what are waves? Your light waves. The light waves will be guided in a medium which is your waveguide. Now, if it is light, it is so it will have a certain frequency. I'll be using usko Sudhir ko bolo na. That board has to be visible. So when we talk about this waveguide, the concept here would be. Just one minute, मैं board पे दिखाऊंगी तो visible होगा. I'm going at a very basic level just to make sure that you all understand the basics, so that when the advanced topics are covered, you all have a good idea about what we are doing. So the first, like I told you, you have your So the first thing that we have is that it has to be guided. What will be the medium in which you will guide the light? So the first component when I say is your waveguide. So when I say waveguide means it will be guiding the waves, right? What is the wave I am talking about is your light waves. So now when you have a signal which is flowing, for example, you have an electrical signal, you have an RF signal, whatever signal, the dimensions of that structure has to support that signal. That is the most important thing, is this device, waveguide, will have a certain structure and it will have a certain material property. It will have a structure and it will have a material property. What will this ensure is the structure of the waveguide and your material property should ensure that light flows in it. Okay? So the first thing is it's an integrated circuit, so it is very compact, small in size. When I am telling it is a compact, small in size means on an average, if you can go and check it, your photonic ICs are generally commercially what it is available or manufactured right now is 2.5 mm cross 2.5 mm or 5 mm cross 5 mm. So this is the dimension in which this circuit is. It's, let's say it is 2.5 cross 5 mm. This is another dimension I have. This is millimeter I am talking about. So that is the whole area in which you will have the circuit. Inside that, what you are doing is, now you are going to put certain components. For example, an electronic IC you have, and I tell you the same area is available. And I tell you that you have to put an op-amp, you have to put a resistor, you have to put a capacitor, all that. What will you have to first thing ensure is, the dimensions of all those components should be able to fit in this area, right? Similarly, when I am coming here to photonic ICs, and I am saying that now I have a photonic IC, I will put certain components here so that light is guided in it. What is the first thing that you have to ensure is, the dimensions here of the waveguides should be such that they fit inside my photonic IC. That is the first thing. Second thing is, when I say structure, what I am saying is my dimension. The second thing what I want to say is that light should be guided. Now, if I make something, let's say I'll say that, okay, my dimensions of, okay, I understood that this is 2.5 mm cross 2.5 mm, and I understood my dimensions would be something in nanometer or something bigger here in micrometer. Then only you can have a whole circuit which is fitting in this, right? If I use anything beyond a nanometer or a micrometer scale device, it will not fit in this area. That is quite understood. Now the thing is, my dimensions I have taken care of. The second thing is, will that support light or not? If I make it out of wood, I can cut a micrometer size of wood and try and use it in this structure. Will it guide light? No, it will not guide light. If I take copper and make it in micrometer dimension structures and say that, okay, now I have dimensions of this structure, let me guide light in it. Will it guide light? No, it will not guide light. So the second thing that you have is your material property. So when I design a waveguide, I have to ensure its dimension and its material property. They are matching. So whenever we talk about, so remember, whenever we talk about photons or light, we all know since childhood we have studied total internal reflection. How does total internal reflection happens? Light goes from denser medium to rarer medium, and it is incident at an angle greater than critical angle for the given pair of media. That medium density, when I am talking about, which parameter I am talking about? Which material parameter is one I am talking about? It is your refractive index of the medium. So, for light to guide in this structure called waveguide, the first component which I have is a waveguide. If light is getting guided in it, what are the two things I have to ensure? First thing is, your dimensions has to be of nanometer or micrometer scale. And the second thing is that it should be having a refractive index or material property so that it is able to guide light. Okay, that is why when I tell you this, we will learn about it. Materials like you will see silicon is the one which will guide. You will have indium phosphide like this. You will learn about certain materials as we progress along the course. But remember that the guiding principle behind using certain material, you will learn about direct band gap, indirect band gap material. You will learn about other such things, 3-5 material, all that. The whole concept of using a certain material is that the material property should be such that it is able to guide light. Okay, so any any channel which you establish, for example, if it is, I am talking about this is a photonic circuit or let's say wireless channel, the channel should be able to support that signal. So always remember that. So then the channel should have a certain structure and the channel should have certain property so that that signal goes in it. Okay, so for example, you have light over here also, right? You can see that light is in this room everywhere. Why can't we use this light for communication? That's the next question. Or why can't we use this light only in the circuit? Is because it is, if you can imagine, if I use this light and try to send it from here to, let's say, from Nagpur to Pune, can I be able to do that? Right? So those are the things. That is why we control this dimension and these properties so that we can send these signals over very long distances. Those are the factors which becomes a deciding. So the first component that is there in your waveguide is, in a photonic circuit, is a waveguide. This waveguide is the equivalent of wires in electric circuit. Just remember that. The most easiest way to remember is, you know what is a waveguide. A waveguide is the most fundamental component in a photonic circuit. It will guide the light waves in my photonic integrated circuit. Now, if it is guiding waves in the photonic integrated circuit, what is the equivalent of it in electrical circuits? Like you have wires. Without wires, you cannot establish any electrical connections. Okay. Now, the way you decide, why do you use copper wires and why don't you use, let's say, this wooden wire, or you can make a wire out of wood also, or foam also. The same reason here. Or what is the dimension there? Everywhere the logic remains the same. You have to have the dimension and the property so that the signal travels in that medium. Okay, so the first component that we have done is, these are the different types of structure that we have. You have ridge, stripped waveguides, slot waveguides. All this we will be covering as we go along in the course. That is, again I told you, this structure when I am changing, when I am saying it is a ridge waveguide, when I am saying it's a stripped waveguide or a slot waveguide, what I am trying to tell you is, this part is what I am trying to control. That is all. Everything is either this material property or the structure. So if I am trying to control the structure so that I can guide wave in my medium. The second thing here is the next component. I am just giving you an overview of this. So as we progress along in the course, you will be going into the depth of this concepts of all these components. The second thing is your coupler. From the name itself, again, what will be it is, coupler means you will be coupling light, that's all. The simple English is waveguide means it is guiding wave, coupler means it is coupling. So now it is given here on the screen, couplers are used for combining, splitting optical signals, making them essential routing within the PIC. So many times what you have to do is, you have to couple light from this, you have to split it 50-50. How will you make sure that this light gets split into 50-50? I want to couple light to one component here and another component here. How will I do that? So there are these components called directional coupler, multi-mode interference coupler. So these couplers will be, again, after waveguide, the next component that becomes important are your couplers for designing your photonic circuits. Yes. So now the next concept that you have is your active and passive components. What is the difference between an active and a passive component? Anyone? Ashay? Yeah. There is a controlling source in case of active, and there will be no such controlling sources in case of passive. Passive means once I have fabricated that structure will remain as it is. You cannot control that. Once I have fabricated one waveguide here, now it will work. You cannot control this waveguide once that fabrication is over. Or a coupler. So these are your passive components. You can send light, that light, whatever is the structure, as per that the light will propagate in your circuit. But Do you not want to control the movement of light in your circuit? Everybody will like to do that, right? Sometimes I want the light should be of a high intensity, sometimes it should be low, I should be modulate it, I should be able to change its amplitude, that is only intensity, I should be able to control that light. That one is the third thing that comes here is your modulator. From the name itself, it tells you is that you can, like I told you, here you can couple, here you can modulate. So when I say you can modulate light means you can, all the modulation schemes that you have studied in your courses, amplitude modulation, frequency modulation, phase modulation, the same thing when I am doing a communication, I am designing a circuit, you have done this, you have studied electronics engineering. When you do digital communication, analog communication, what you do amplitude modulation, you do amplitude shift keying, you do BPSK, QPSK, all those modulation. How do you do that? You have a certain electrical signal, you have a message signal, you have a carrier signal. After that, you give it to a modulator and you will have a modulated signal. Right? This is the whole concept of modulation in your digital communication. Everybody has done this, right? What you do is you take certain information, you put it on a carrier, you modulate, and then you send it for communication. Again, when I reach the receiver here, you will have a modulated signal, you will demodulate and extract your message out of it. This is a simple concept that we have used in all the communication. What am I going to do here now is, I have message signal remains the same. It is your information. Information is what I am saying and it is getting telecasted everywhere in the country. That is my message. What will change is this is your carrier signal. What will be the carrier? Previously when you do the communications which you have done, when it is electronic and communication engineering, you are using electronic circuits and communicating, right? Now what I am telling is it's a photonic circuits. So basically you will be using photonic circuits for communication. So what will change is this carrier signal here. The message remains the same, your song, your music, your whatever it is. Carrier here becomes your light signal or your photons here. This is what is going to happen. That is the only thing that is going to. So now what should the modulator do? Previously case, your modulator was able to take a message signal, it was a carrier signal, and then it was able to modulate it and get an electronic circuit. Here what is going to happen is, this modulator will be optical, it will generate an optically modulated signal. Why? Because my carrier is now an optical signal, it is no longer an electrical signal. That is how the whole thing has to work. So this modulator will now work such that it can control photons, not electrons. So electronic circuits, electrons were getting modulated, now it is photons which has to be modulated. So this is a active component that we have here. This is an active component. Why is it an active component? You can control this. You can give a certain, all of you have studied, you give a bias to it, modulation you have studied, the various forms of modulation schemes and everything. Here also you can do that. So when we have the hands-on session, we'll show you basically, our students have done this, we'll show you how to use a modulator so that you can get optically modulated signal in your ear. Okay. So over here you have these examples here, electro-optic modulators, silicon-based modulators, all this you will be covering as we go in the course. Now the next component that we talk about here is here. Okay. Achha. Yes, ये भी idea. Yeah, perfect. हाँ ठीक है ठीक है. ये तो दिख रहा है ना? नहीं इसे करना. किसमें zoom होता है? Now what I have been doing is, I have light, I have sent the light, I have coupled it, I have modulated it. The last thing that I have to do is, now I told you, in your modulators, when you have this whole modulation scheme, you have a message signal, you have a carrier signal. Over here, what is the purpose? You get your modulated signal. Over here, you want to demodulate it. You want to demodulate it and extract your original message out. This is the whole purpose of communication, right? I have my message, I modulated, got a modulated signal at the receiver. This is your transmitter end, this is your receiver end. Receiver end, I will get or extract my message out of it. What will be the first thing? Message is your electrical signal, right? Message is a basic baseband signal. All of you know that. So that's it. What is the, now how will I convert? So the question that arises is, I will have to convert my optical. So this till here, once I have, this is optical. And this final here is electrical. So how will I convert that optical signal back to electrical form? That is, then only I can get my message extracted. So what is that? That component is known as photo detectors. This you have done is in your course, all the courses of even your electronics, diodes, photo detectors. What is it? The electrons will, the photons will fall on it, electron hole pair will be generated like a reverse bias diode. What happens? Your electrons falls on it, electron hole pair is generated and current will flow in the circuit. So that is the simple concept here. So that also has to be available so that you can convert your optical back to the modulated electrical form so that I get my message signal back for my purpose. Okay. Next thing is your obviously the sources that you have. So the sources basically, how can you generate light? That's the first thing that you have. The whole thing you understood. You can guide light, you can couple light, you can modulate light, you can, photo detector means you can detect photons. Obviously, now that is the thing that topic that we have here is, how will you generate light? Right? Like I told you, you can generate light from hundreds of sources, right? Sun is the biggest source of light, right? Can we use that for our why? The whole thing is in this dimension, I have to fit something which generates light for me. That is the option. I have bulb, I have candle, I have hundreds of sources of light in this world. Can I use that for my photonic circuits? No. Why? Because my whole dimension is here. In this, I have to make sure that light gets generated, it gets guided, it gets coupled, it gets detected. So, how will I generate light or the light sources here? That is what is the next thing. There is your, light sources. Okay, so some light sources which are used in, you have learned about it, students. Light emitting diodes, lasers. Have you learned about it? Laser stands for light amplification by simulated emission of radiation. Those are your, now what is the challenge when it comes to photonic circuits is, your light sources which are available currently, you have lasers, you have LEDs, you can go and check, optical labs are there nowadays in all the colleges. They are quite big. Right, the dimension will be any day bigger than this dimension of a chip. So what is the challenge is, light sources will be to bring it to the dimension of your photonic IC so that I can have it on chip. Another option that we have is, I keep my source outside and from there I get it to the chip. So that is, there are two types of sources, off chip and on chip. Understood? Very simple English. Off chip means my light source is outside the chip. From there I am sending the light in my A. On chip means my light source is on the chip itself. Now what will be the advantage of on chip is, your light is, your whole circuit is in this compact A. What is the advantage, but what is the challenge associated with it is, you have to have a very, very small laser which will be in the dimensions of micrometer, which is Very challenging to have it. There are technologies, there are companies which are working, there is called indium phosphide technology. You will learn about it. In indium phosphide technology, you have that laser on chip. But that is very challenging. Then all the components have to be in that. We will learn about the technologies as we go ahead. But if you do not have a light source which is on chip, what is the other option is? You keep your laser source off chip. Generate the light, put it on the chip, and then you guide it, you couple it, you modulate it, you detect it, and you design your whole photonic circuits. So these are your, other than this, there are other, obviously you need number. For example, if you have studied electronic circuit courses, you have number, it's not that you just have a resistor, capacitor and inductor. You have hundreds of ICs available, right? Similarly, here you have other hundreds of components also available. Like sir will be, they are tailor-made components which are designed so that photons can go move in that component, and then you can achieve some purpose out of it. For example, you have a BJT and a FET, but you also have operational amplifiers or op-amp, right? Another component here. Similarly, you will have components here like micro ring resonator. Sir will be telling you about this, Professor Pavesi will be telling you about this, how it's a very versatile device, micro ring resonator. You can control it, you can make it active, you can make it passive, all that. So there will be other components also as we optical or photonic circuit PIC components that we will be studying as we progress. So that does not this, I was just giving you an overview of how to design a photonic ICs. For that there are certain basic components. You will have a light source, you will guide the light source using a waveguide, you will couple it, you will modulate it, you will detect it, and then there will be other active, not just, I have written here optical or PIC components. There will be other active and passive components which are available. So some of it, like sir will be covering in the class as we have our, as we progress with it. It's a 1 week course, so you'll be learning about them. What else will you do is, you will be doing the hands-on. When you do the hands-on, when we do the practical, there also, see, it's not possible that in a 1 week's time we tell you everything. So as we introduce certain components in the simulation, for example, I told you we have a simulation software, we'll be simulating photonic ICs. So once I am simulating that photonic IC, at that time I will be using certain components. If we have not covered here, we cover it here. That time what you do is you explore about it a little bit. We will be telling you during the day that these are the components which you will use, like the way you do your practicals. When you do your practicals and you are told, okay, take this component, that component and design a circuit. If you don't know the name, you just read the name, you find out, okay, you know it very well, IC741. If I say it's IC741, you automatically know it, it's an op-amp. You will automatically understand. But if you don't know it, what will you do? You will study about it, you will Google it, and you can understand. So as we progress along the course, as we design this, the simulations and all, we will be learning about more photonic circuit components in the year. Okay. Any question till now? I'm just giving you a brief about it. Yes. So the now at least we have a picture of what is a photonic integrated circuit. We are guiding for photons in it. We know what are the components which are present in my photonic integrated circuit. There are certain active passive components. We have light sources, we have detectors, we have modulators, everything. Now the next question that comes is a technology. When I say a technology, what do I mean is, when I say that the structure will have certain dimension and a property, okay, now there are hundreds of such materials available which will, even let's say I'm telling about these which will guide light, right? For example, you have a technology, you can have, like you have done total internal reflection, right? Light goes from denser medium inside to a rarer medium outside. Inside you have studied about optical fiber in high school physics, everybody. Have you done that optical fiber? You have something at the center and then this is outside and you have, it guides light. So here this is what you call a core and this is what you call a cladding. Okay. You can use certain material in the core, you can use certain material in the cladding. Once you use that, for example, I use silicon in the core and SiO2 in the cladding, and I give certain dimensions to it, light will go in an optical fiber. I come here, I tell you that it's a waveguide. Again, I have a core and this is the cladding of my waveguide. The structure has changed, we'll see this when we do RA, and I'm designing a waveguide. Now the thing is that this is a commercial, like I told you that we are having a lot of research in it, this technology is developing, companies are interested in this, all that we have read about it, right? Now what happens is when the this technology is getting commercialized. When I say this, that it is getting commercialized, you have to develop certain standards for it, right? You know what is an op-amp, but an op-amp can be of different, you have IC741, there are number of numbers that is given to it, right? Though all of those numbers or IC number, when you see, they will all behave like an op-amp, but when it comes to commercializing or whenever it comes to developing the technology, we give specific names to it. So yes, I can guide light if I have a core of higher refractive index compared to cladding, all that I have understood. But the moment an industry comes into picture, you have to fabricate. I told you that you have to simulate, you have to fabricate, all that you have to do. Now the question is, if I have to do that, I have to standardize it. Right, that's the first thing. You have to stand, whenever you have, for example, you have read about wireless communication, mobiles, everything. But there are protocols which you have to follow, right? There are wireless communication standards, that IEEE standards. Those have to be defined. Similarly, here when I come, I know everything, but once I want to commercialize it or standardize it, I will have certain standard technologies available. What do I mean with the standard technology is, first example which I take is a silicon photonics technology, which is the name which I have given to this course. What does that mean is, now my core will be having silicon here and around this a material, because I already worked in this field for many years, I know it will be SiO2. So this technology, now when I send it to any company for fabrication, like tomorrow that company is giving a demo of the tools, they will say that, which technology are you using to design your circuit? What do I tell them at that time? I'm using, let's say, silicon photonics technology. The moment they know that it's a silicon photonics technology, they will understand that. After that, I don't have to explain anything to them. What they will understand is, all this waveguide, coupler, modulator, detectors, everything, the core will be silicon, and around that you will have SiO2 in this. So like that, certain technologies have been developed in this field of photonic integrated circuit. So the first thing I told you, how they have developed, that also as we progress along the course, you will come to know. The reason why it is silicon means why light is guided in silicon and why light will be guided in indium phosphide or whatever technology it is. But before we go in that, the standard commercial name that is given to these technologies, once you interact with any company around the world, like okay, you want to talk to Finisar, they are designing a laser. This is a company which is there, it is based in Hyderabad, it's a multinational company, they have opened it in Hyderabad. They only work in indium phosphide technology. So once they tell that, okay, we are working in PICs and we are designing lasers for PIC using indium phosphide technology. Once they tell you that, you say here, okay, my core will be indium phosphide here. This core becomes indium phosphide and outside cladding will be a material of indium gallium arsenic phosphide. We know that. But once you tell the name of the technology, immediately the company or your user or whoever is at the other side of the table, they will know that all this is made from that material. For example, if I tell you helium neon laser, what does that mean? Even if you don't know anything, you know that the active material in helium neon laser will be helium neon. If it is a ruby laser, even if you don't know anything about laser, once you tell the material or the technology name, you know that that will be the active material of that technology. Similarly, here in PICs, as we are now going into commercialization and standardizations, we have all these names that are coming up. That is, first is your silicon photonics. When I say silicon photonics, my core is silicon. When I say indium phosphide, my core is indium phosphide. When I say silicon nitride, so tomorrow when we will show you these, we'll show you companies who are working around the world, who are working in these technology. So the moment they tell you that, okay, there is a company which is coming up in Italy, it is working in silicon nitride technology. What will you implement from that is that, okay, the core of all the components that they are developing is silicon nitride. Along that, you will have another cladding of lower refractive index material. But you will automatically understand that. Okay. Then there are hybrid platforms. Okay. So we will end it here. We'll again start, we'll have a short tea break first. So the summary of it, what we have, one minute. So the summary of it, as of now, as we begin with the course, at least now you have a picture of what are the different types of, what we will be covering. First, I have told you in this course that we will be covering the silicon integrated photonic circuits for quantum communication. That is, so that is how this course will be. Then what is photonic integrated circuit? I told you, I gave you a very good example, compare it with electronic circuits, and we designed it that. Then if you design any circuit, what are the different types of components you will use? You have been studying electronic circuits, coming to photonic circuits, these are the components that we will be studying here. The third thing which I told you about are the different types of technologies. Once it is a standard commercialized product, then you have to be very sure that what technology you are going to use. Then that those terminologies we have covered. The only thing is, it is the material which you will be using and the structure. Like I told you, the structure and the material, that defines your technology that will be used. Okay, we'll take it again. So we have a colleague with us, Professor Joydeep Singh Gupta. He will be telling a little bit about his Gian course for all your participants, and then we will have a tea break of half an hour. Again from 12 to 1 we will have another session, and 1 onwards we'll have lunch break. Okay, so we are providing lunch to all the participants. Please have a good time that time. And we can discuss the doubts. If you are not asking now, we can discuss it that time.
Hello. So good morning to all. Actually, there are another GAN course we will conduct in the month of June. The date is from June 23rd to 28, 2025. And the title of the course is Machine Learning Application for Automation Engineering. So the foreign speaker is from University of British Columbia. He is Bhushan Gopalini. And me and Dr. K. Surendra, the coordinator of VNIT. So I am keeping this flyer here, registration disc. Please collect it, and if anyone want to join, he or she can join. Okay, thank you.
Okay. Yeah, please. So this course is relevant to the machine learning. So even though it's relevant to the application is relevant to the automation, but you could able to learn all the automation, all the machine learning algorithms with related to the application of automation. So that will be the hands-on session will be there. The faculty is from University of Columbia, so and he is associate dean at there. So it would be a good interaction if you could are able to join some more people who are working in control, automation, instrumentation, variety of fields like this. Okay, it's a machine learning course. Yeah, please forward to your colleagues. Thank you.